First, our problem description. Search an ordered array. Yeah. Our problem number 11. Here, this information is important. Ordered array. Yeah. If it's unordered, then we can only use linear search. We learned before linear search in our module 1. Yeah, that's for unordered array. But now we organize the data. We make our data organized. Yeah. Usually this step is very expensive. That means you need to do sorting, right? How do you make ordered data? Given original data usually unordered. Yeah. If you want to make it ordered, you need to pay some quite expensive cost with that data organization, that step usually quite expensive. Yeah. After you pay that part, we can treat as investment because the rewarding is much bigger than the amount of time we pay. After that, we can take advantage of the property of our data because we have organized the data. That property we can take advantage of to make our algorithms more efficient. So this binary search, we want to take advantage of this ordered data property. Okay. All right, first let me describe the problem. Given an ordered array and a search key V. Okay, yeah. Question, how to find an index I such that V equals A of I? Yeah. Here you can see this problem description very similar to the one for our linear search problem. The only difference is we changed the unordered word to ordered array here, that word. Only one word change. So we get this problem number 11. Yeah. All right. So the main question, we need to find a solution by taking advantage of this new property. Yeah. Data, ordered data property. Yeah. All right. Let's do analysis. Yeah. Here, how to take advantage of this ordered property? Yeah, so that's the most important thing we need to do. Yeah, the idea we use our old idea, reduce the problem size by the ordered data property. Reduce the problem size. We used this way many times before. Yeah. The question is how to reduce the problem size. Right? How to reduce the problem size. Here we have the important ordered data property. So we want to use this property to reduce the problem size as much as we can. Yeah. So that's the basic idea. Or we can treat as the strategy. Yeah. So this is the strategy we want to take. All right, by elimination method. Yeah, elimination. Yeah, how to do elimination? Yeah, so let's look at the details. Yeah, how can we take advantage? Yeah, all right, we need to explore the order property. Yeah, okay, yeah. All right, so here let's consider a typical situation. Yeah. But this array is ordered. Yeah. So that information is important. Yeah. Now we want to find the location for this V key. Yeah. Where can we find this key in a given array? Which location? Okay, yeah. We can do comparisons here. We can do comparisons. Here, I show you one example, one special case, we do the comparison. Here, these two arrows means we compare V with last element A sub n minus 1. Our first try. When we do our first comparison, this is our first try. Okay. Then let's consider what is the possible results we may have after this comparison. Similarly, we can compare this V with any element in this array. And we need to look at after one comparison, how much progress can we make? We want to see that after one comparison, how much progress we can make. Okay, yeah. All right. Question, after one comparison, how many elements can be eliminated? So that's the elimination method we are using in this situation. Okay, yeah. All right. Let's look at the first special case when we compare V with the last element A sub n minus 1. There are two possibilities. The first one, the best case, V is greater than A sub n minus 1. Is greater than. Or we can say greater or equal, including the equal, because when V equals the last element, it's also the best case. The best case, it means after one comparison, we get the search result. That's the best case. Only one comparison, we can make our conclusion. We can make our conclusion. The conclusion is, if V equals to the last element, then we find it. We can return the index I for which A of I equals V. That's the solution. Or another case, V strictly greater than the last element, then we can also make our conclusion. This array does not contain the element of V, and we can tell the location of this V. This V is greater than the values of all the elements in the given array. So we have that conclusion. So that's the best case. One comparison, we can make that conclusion. Another case, other cases, V less than A sub n minus 1. Yes. So you can see we have two possibilities. The first possibility, the best case. The second possibility, V less than A sub n minus 1. That means we need to do more comparisons. For this situation, we need to do more comparisons. We can eliminate, in this case, we can eliminate the last element. This A sub n minus 1, we can do the elimination, but still we need to consider V in the first n minus 1 elements. We need to consider that case. First n minus 1 elements. Still, we need to find the location for this V. A lot of work we need to do. All right. Here, by this first try experiment, do you have any useful information you can discover by this first try. Yeah. So let's see. Yeah. Murphy's law. Here, I like to, talk about the Murphy's law. Yeah. Why first, the Murphy's law, right? Yeah. From your real life experience, people, talk about the Murphy's law. So what's that? Anything that can go wrong will go wrong. Okay? Yeah. So here, what do you mean here, Murphy's law here? Because the best case, that's something we like to have. This part, that means we need to do a lot more work, We don't want to see this case. We want to see the best case. So this case for us, it means something go wrong, right? And we want to avoid that could go wrong. But based on Murphy's law, that can go wrong, okay? That can go wrong. So that means we need to focus on this wrong case, okay? Something wrong, this wrong case we need to focus on. Best case, we don't worry about it, okay? We like to have it, yeah, we don't worry about it. But the wrong part, that's we need to really, do a lot more effort to find a solution for that wrong part, okay? Yeah. So here you can see from the problem size reduction point of view, reduce the problem size. From the problem size reduction point of view, how much size, after one comparison, how much size we do the reduction? Only one. We only eliminate one element. That reduction is too small, right? So this reduction, too small. So that's not a good reduction way, okay? Yeah. Definitely, we want to do better, faster reduction than this one, right? Yeah. So our next round experiment, we want to do better than that, okay? Yeah. So compare the element right in the middle. Yeah. All right, right in the middle. We call it a median. Yeah, so median. Yeah. Here regarding the median, yeah. So what's the definition of median? What's the definition of the median? Right? Yeah. So sometimes some students ask me this question. Yeah. We know the definition for the median. If you sort that array, the one right in the middle position, it is the median. Yeah. For all the number of elements, then you have no problem. Suppose you have all the number of elements. The one in the middle, there is no argument, right? Yeah. So there is one in the middle, absolute middle. Yeah. Nobody can argue with that. But when you have even number of elements, then which element we call it the median? Because there are two elements, they are in the same position with respect to the middle, in the sense of middle position, right? Yeah. So usually we call the left median. Yeah. So the left one, we can call the left median. The right one we call the right median. Okay. Yeah. So you can see there are two median, but left median is the default median. Okay. Left median is the default median. Yeah. That means if we do not say left median or right median, we just say median, we refer to the left median. Okay, yeah. Because in that way, there is no confusion. Otherwise, people always ask us, what do you mean the median? Do you mean the left median or the right median? Yeah. By default, we mean the left median. Okay, so then there is no uncertainty. Okay, everything is clear. No matter we have even number of elements or all the number of elements in the given array. Okay, all right, so after we have this median concept, yeah. Then next, oh yes, strategy, yeah, balancing principle, yeah. So here next, right. So this idea, yeah, every time you can throw away 1/2 of the elements. Yeah, so this idea, let's talk about next. Yeah, next. All right. Yeah, efficiency. Yeah, right. Here, let me use this diagram to show you the idea. Okay, yeah. So the best way for the elimination, when we choose an element somewhere in the middle of the array to do comparison, to do our first comparison, the middle one gives us the best possible result. Can you see that? Can you see this property? Yeah. When you choose the median, here, let's assume this is the median, okay? Yeah. When you choose the median element as for your first comparison, you can get the best possible result. Why? Why? Okay, yeah. So here the idea is pretty simple. Because after one comparison, you can drop one of the two subarrays, either the left subarray or the right subarray, right? You can drop one of the two subarrays, right? Based on your comparison result. Yeah. If the median is, yeah, let's say the median, yeah, let me use M. The median is greater than V, greater or equal to V. If your comparison tells you M greater or equal to V, that means the left subarray can be dropped, right? That means, yeah, because if it equals, yeah, let's say, if it equals, you get a solution, all right? Yeah, let's consider. If equals, you already have the solution. You stop. After you find the solution, you should stop, right? Yeah. So we only consider M greater than V. If M greater than, you can drop the whole left half subarray containing the median. Okay, so you only need to consider the right subarray, excluding the median. All right. Similarly, if M less than V, you can drop the right half of the subarray. Yeah. So the problem size reduction, you can reduce approximately 1/2 of the problem size, right? Approximately 1/2 of the problem size. But think about, if you do not compare with the element in the right in the middle, yeah, let's say, suppose this is your array. If you compare the element approximately 1/3 of the right, counting from the right end, 1/3, although you have a chance to drop the bigger subarray, but you have another chance to drop the smaller subarray. Think about that. You have smaller chance to drop smaller subarray. That means 1/3 original problem size. That reduction is slower than 1/2 of the problem size, right? Here we drop the 1/2 of the problem size, but here you may drop 1/3 of the problem size. That means your problem size reduction is slower than this medium way. Medium way is faster. Okay, yeah. So that tells us this medium way is the best way. Overall best way. Okay, yeah. All right. Now, next round, yeah, because after one comparison, so think about that. After one comparison, we reduce the problem size by 1/2. Okay, let's do another comparison, our second comparison. We reduce the problem size by another 1/2, drop another 1/2 of the current array size, and so on. So we keep doing that, and after certain number of comparisons, the array size is reduced to this small. How about that? Here, I use this table to show the data size we have after each comparison. Yeah. After the first comparison, the data size becomes n/2. Second, it becomes n/4, and so on. After k comparisons, the problem size or the data size becomes n/2 to the kth power. Yeah, so that's what we can get after our elimination methods. Here we use the elimination method. That's what we can get.